All right, so in this video, we're going to take a look at a few examples here dealing with integration using this idea of partial fraction decomposition that we looked at in the last video. Now that we're past the algebra of it, we can focus in on how to apply this now to our integral. So when you see a problem like this, as always, take a look at it and see if you can integrate using earlier and much easier techniques. Unfortunately, this one doesn't look like that's the case. So being a rational function with a numerator and denominator, I'm going to go ahead and factor that denominator completely. Now, in addition to that, I'm also going to take out this 5 from the numerator. That's an optional step here, but I'm a big fan of always taking out those unnecessary constants if I can. So that denominator is going to factor into 3x plus 1 times x minus 3. And so now we're ready to take this x minus 1 over the 3x plus 1, x minus 3, and decompose it. So since I have two factors, I'm going to have two things that I add together. Both of these are linear, which mean that once I drop in the 3x plus 1, I'll have a constant on top. Same with an x minus 3. I'll have a constant on top. Now from here, if we put this back together, we would get an a times x minus 3 plus b times 3x plus 1, all still over that LCD of 3x plus 1 times x minus 3. And so now we're going to set this equal to this. That's the next step in this process that wasn't really talked much about in the previous video. But now we'll take those two boxed in things and set them equal to one another. So I'm going to have this ax minus 3a plus 3bx plus b set equal to x minus 1. So now I'm going to take a look at the coefficients, and that's what's going to give me my system. For starters, I've got an ax, 3bx, and then on the right hand side I have this 1x. So right now I'm focusing just on this, and this. And from that idea, we know that a plus 3b has to equal a 1. That 1 that I'm talking about right here is going to be the coefficient, right? When you combine like terms, you combine by adding the coefficients in the front, and then of course you still have the 1 on this side that we would then set equal to, okay? Now similarly, we would have this negative 3a plus b, both of which are constants, set equal to the constant on the right side. So we would have this negative 3a plus b equals a negative 1. So in this case, we have a 2 by 2 linear system that we would solve for a and b. So if you do this, and I'm not going to solve a 2 by 2 linear system on the video, you can use substitution or elimination, whichever you prefer. We would find out that a equals 2/5 and that b equals 1/5. So now I'm going to take both the a and the b, and I'm going to plug them in here and here. And then remembering that this is an integral, I'll be able to hopefully configure this in such a way that it's much, much easier to work with. So I've got my 5 out in front still. I've got an integral of 2/5 over 3x plus 1 plus 1/5 over x minus 3. Now, if I clean this up just a little bit into two separate integrals, I would have 2 with the integral of 1 over 3x plus 1, then plus the integral of 1 over x minus 3 dx. So the whole idea of being able to take something that originally you couldn't integrate very easily, decomposing it into two now smaller things that we can integrate very easily, was done by this partial fraction decomposition process. This part's what we discussed in that first video. Now we've taken this step further to set up the actual equality and then the system right here. All right, so now we can integrate as usual. This is going to be a 2/3 natural log absolute value 3x plus 1, and then plus the natural log of the absolute value x minus 3, of course, plus c. Both of those integrals are done by either writing out the u substitution or by having done so many of these to this point where you feel comfortable going directly from here into here. But either way, both were a u sub to get us down to this point. Okay, so on our next problem here, first thing that you should notice is not only are you dealing with a rational function, and it doesn't appear that any of the earlier techniques are going to work, but in addition to that, that you're dealing with an improper fraction. We have an x to the fifth on top and an x cubed on bottom. So no matter what, with partial fraction decomposition, the whole idea is to decompose it into smaller things that we're able to work with a bit more easily. But there's other algebra that can be applied here to do the same thing, at least for part of the problem. And since, again, it's an improper fraction, we can simply use our polynomial long division to divide this and hopefully get a quotient that's going to be easier to integrate, and then we can worry about the remainder a little bit later. So I'm going to use some division here. I'm going to take this x to the fifth, and don't forget your placeholders here, plus 0 x to the fourth minus 4x cubed plus 0x squared plus 0x plus 1. That's all going to be divided by this x cubed minus 4x. And so as we start this process, we'll ask ourselves the question, what times x cubed is going to give us x to the fifth? Well, that would be an x squared, keeping our columns aligned. Now we'd have an x to the fifth minus a 4x cubed. All right, so we'll remember to subtract everything now. And that actually zeroes out everything except this 1, which would then be our remainder. So we would have a plus 1 over x cubed minus 4x. Now, it might not have seemed like it did a lot for us, but it did do something. Now when we're ready to integrate this, we're going to have this x squared plus 1 over x cubed minus 4x dx, where at least we can see from this guy we get a 1/3 x cubed. So at least it broke off part of it for us, but now our primary focus is going to be how to finish out the rest of this problem, specifically this integral right here. Now, due to space constraints, I'm going to go ahead and delete the synthetic division here, and then I'll move back over to this side of the page. Okay, so all I've done again is I've taken this guy and I've moved it over here. You can see that that denominator would factor. You could take an x out, and then it would leave us with an x plus 2 and an x minus 2 once we factor the difference of squares. So now it looks like we're ready to move forward with partial fraction decomposition on this guy right here. So I've got my 1 over x, x plus 2, x minus 2. There are 3 factors, so I'm going to have 3 things that I'm going to add together. Of my x, x plus 2, and x minus 2. All 3 are linear, so we're going to have constants a, b, and c in the numerator. And then as I put this together now, this is going to be an a times x squared minus 4 plus b times x minus 2 plus c times x plus 2 all over the x plus 2, and x minus 2. All right, so now we're going to take these two things here and set them equal to one another. As I do this, I'm also going to distribute as I need to through here. So all of this then will be set equal to that 1. All right, so in doing this, I'll have my ax squared minus 4a plus bx squared minus 2bx plus cx squared plus 2cx equals 1. All right, so now if we focus on our coefficients, our x squareds. From this, we can see that a plus b plus c would end up equaling 0. There are no terms over here with an x squared, so you could picture this as a 0x squared. That's why we're taking all 3 of these and setting them equal to 0. All right, so we'll go a little further now with the x's. We've got minus 2b plus 2c is also going to equal 0, since again there's no x term over here. And then finally we have this minus 4a must be set equal to 1. And so there sits our 3 by 3 system. So even though this one has an additional variable in it, an additional equation, it's still actually very simple to solve. Again, I'm not going to waste a whole lot of time in the video talking about that, but I will summarize by saying that a equals negative 1/4, b equals a 1/8, and c also equals a 1/8. So I'm going to take these constants right here, plug them in there, and there, and then integrate all three of them separately. So this one's going to look now something like this. I'm going to have my 1/3 x cubed from above, and then plus the integral of negative 1/4 over x dx, plus the integral of 1/8 over x plus 2 dx, and then plus the integral of 1/8 over x minus 2 dx. And so might clean this up just a little bit if you want to. However you handle these at this point, I feel is kind of up to you. So all I'm doing right now is taking out the constants, and then we'll integrate as usual. This will be a minus 1/4 natural log absolute value of x, plus a 1/8 natural log absolute value x plus 2, and then plus a 1/8 natural log absolute value x minus 2 plus c. So those integrals respectively where it was just a natural log direct, and then a u sub to a natural log and a u sub to a natural log. There's a chance, and then you can do this on your written work as well, but you can combine these. So if my math lab is looking for this to be combined, you can use your properties of logs to do so. Otherwise, this would be a perfectly acceptable final answer.